Okay, welcome. This is Chapter 1. Okay, I mentioned to you guys in the introductory videos, the way I do it is I basically go through my lecture notes and I got some graphs and to help out, but that's about it. So you have to have the book to be able to follow along. Okay, let's start. So, learning objectives on page 1. And they talk about all sorts of cool things like learning how to analyze and, what the rate of growth is and all those kind of cool things. Worst case, best case, average case, and all those. A decision tree. Lots of good stuff in there. And yes, when you get to the end of this chapter, you should be able to do all those things. So let's just start with the basics. When it comes time to analyze an algorithm, the first thing that's going to have to happen is the algorithm is going to have to work. I mean, that's a given, right? You can't analyze something that doesn't function. And then the question is, how efficient is it? Now, some people, efficiency is all about speed. And okay, that's typically the correct answer. But sometimes if you can speed things up to the point where obscuring what it is that it's doing, so it makes it totally unmanageable and totally unable for other people to come behind you and work with the stuff that you left behind because it's just totally Greek. So that's not always the goal, is to speed things up to its ultimate. No, you want it to be maintainable as well. So we are going to be spending time on which algorithms are the most appropriate given a particular scenario. I mean, for example, we're going to be doing like a half a dozen or so sort routines, but when you get to the end, you're going to have to know, well, if it's this kind of data, I need this sort. If it's this kind of data, I need that sort. That's what you're supposed to be learning in this course. So the actual amount of time it takes, stopwatch time, isn't all that relevant, to tell you the truth, because that's dependent on, your machine and how much memory you got and what kind of processor you got. What we're trying to do is compare the execution times. So again, using sort as an example, if one sort did it in 15 seconds and the other sort on the same machine did it in 30 seconds, well, you learned that this one is twice as fast as that one. The 15 and the 30 are not relevant. The actual execution time is not what we're after here. We're after comparing execution times between different sort routines as an example. Okay, on page 2, they talk about what is analysis? Well, there is created an estimate for how long it'll take for a known number of values to be run as input. So how long is it going to take to sort 100 numbers? That's a good example. Now again, how long sometimes could be stopwatch time. It's going to take 11 seconds. Or it could be just a notation. And we're going to be talking about the big O notation a lot. So there's a mathematical way to describe the complexity and how much time it takes for a sort routine to work, and using a mathematical formula that we'll get to in just a minute. Okay, so remember I talked about not always do you have to go for speed and speed alone. So this is an example on page 3. So here's a way to find the largest number. This is pseudocode. By the way, one of the tasks you're going to have in this course is to convert pseudocode. So the textbook's got some pseudocode. I'm going to supplement it with some additional pseudocode. And I do absolutely positively want you to convert the pseudocode into whatever language that you're using. If you recall from the introductory video, I don't really care what the language is. I mean, you could be using Java or C++ or, Pascal or Python or whatever, C#, doesn't matter to me. But either way, this is what's going to show up in the book. So the one on the left, it actually is just as efficient as the one on the right. If you were to actually go in there and count the number of comparisons that it would take to find the largest of 3 numbers, they actually come out the same. These are computationally equivalent. However, the one on the right is confusing and, quite frankly, unnecessarily complex. So I wouldn't use that one. I would use the one on the right because it's just doggone simple. Okay, so yes, the one on the left is easier to read, and it uses a temporary variable. Now, yes, the one on the right doesn't have any temporary variables, okay? And the one on the left uses a temporary variable, but it sure makes it a lot easier. So we're trading off a tiny, tiny bit of memory to make this thing more readable. Now, is that going to be a performance hit? Creating this variable called largest? Nah, no. If we were to stopwatch these guys, they would come out about the same. So, one more time. Both of these take the same amount of time to run. And if you don't believe me, just actually go through and figure it out. Just randomly pick which one you think, like C. I want C to be the larger. And count the number of comparisons, okay? And the number of comparisons on the left and the right are identical. And the comparisons is where the majority of the energy is going to be taking place in this application. Okay, so one more time. The goal of analysis is not to predict the absolute accurate execution time, clock time. That is not its goal. Its goal is to produce a number which you can use to compare to another number. So if we had stopwatched this guy, we would have determined that these two are roughly equivalent. Okay, there's another example coming up on page 3 and 4. And this one is about reading a file of some sort, where I start off with I zero out an array. I have some sort of an array of 256 characters, and I assign 0 to all those guys. And then while I'm reading a file, I get the character and then increment it if the whatever character that is, it counts. So this is going to count the number of A's, the number of B's, the number of C's. That's all it does. Okay. Now, if you look at this, the number of increments, the number of assignments that take place, and the number of conditional checks to see if things happen. So N is the number of characters in the file. So if the file had 100 characters in it, okay, you following me? Then that would be 256 increments, right? The number of assignments stays the same, and the conditional checks would be 358, okay? So those things that increment, that takes energy, so to speak. It takes time. Assignments take time. Conditional checks take time. And so this is a way to count. But if I was to go further, let's say the file has 500 characters in it. So that's 1,771 operations. But if it had 50,000, not 500, but 50,000, it'd be 100,771. So, wait a minute, that's not exactly, going from 500 to 50,000, wouldn't you think that it would be just like take the 1771 and add some zeros at the end? So this thing is not linear. In other words, the amount of computation changes when the value for N goes up. So, the percent of operations that actually do work, okay, the amount of operations that do work is not the same. Okay, so when you add more things to sort, the sort's going to take longer, right? It kind of makes sense? Okay, good. So there's some things that do work and some things that do not. For example, at the very beginning where we're taking all 256 characters and we're assigning them all to 0. I mean, that's a necessary step, don't get me wrong. But that's not directly associated with reading the file, getting the character, and then incrementing the count. Okay? So that's sort of like overhead. Okay. All right. On page 7, they talk about input classes. So an input class, here's yet another example of taking an array and finding the largest item in an array. Okay, they start off with the first array element. By the way, in their pseudocode world, arrays start at 1. Okay, now in none of the programming languages that we deal with, that's the case. They're always start at 0. So you're going to have to learn how to go through and change, like this 1 should go to 0 and this 2 should go to 1, and anyway. So yes, translating the pseudocode into something that's actual real code, like that will work for Java, is going to be one of the things you're going to have to learn. Okay, so if I was to give this just goes through and figures out which one is the largest, okay? And if it's largest, it goes through. Now, if this was already sorted, okay? If it was already sorted, then this comparison operator would only run like at the very, 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 very end, okay? Like it would run one time. Now, if it was completely random and you had an array of 100 elements in it, then the average would probably be around 50. Are you seeing what I'm saying? Okay? In other words, this statement right here would probably run 50 times if it was a completely random. If it was pre-sorted, it'll probably run one time. Okay? So the input class, that's the term that they use to describe the type of data that we're dealing with. The input class has a tremendous amount of impact on evaluating the performance. If someone said, "What's the performance of this algorithm?" you'd go, "I can't answer that question because you haven't told me what the input class is." Okay? Good. All right. So later on, like for example, I always use sort as an example because it just comes in handy. So later when we do sorts, we're going to do a sort that's completely random. We're going to do one that's kind of sort of pre-sorted, but not really. We're going to have one that really, really is sorted. And so, yes, we're going to be able to test these inputs. Okay. So moving on space complexity. That sounds almost like a science fiction show or something, but no, on page 8 they talk about how much memory that an algorithm uses. Okay, now this one has one variable that's being used, so its memory is relatively low, right? But let's go back and look at this guy. This guy's going to have probably build an array of 256, so I mean that's not a heck of a lot of memory, but hey, it's 256 times more memory than this guy. All right, so again, we're comparing, right? So this guy uses, like one local variable, and that's it, called largest. And this guy has some sort of an array with 256 characters in it. So this one is significantly larger than the other. So space complexity is the term they used for how much memory that we're using. So, for example, some of the sort routines do an in-place sort. In other words, I have an array of 100 characters, or 100 numbers, and I want to sort them. It just moves things around inside the array until everything lines up. There's another type of sort which builds a second copy and starts putting things in this second array, and it puts them in the correct location. Now, it's probably faster, but that means it consumes twice as much memory as the other technique, because I have to have two copies of the array. The original array, and then the second array of 100 characters each, right? Okay. So, space complexity is the term that they use to describe how much memory an algorithm is going to use. And once again, it's used for comparison. There's no this is a unitless number. It's like 12. 12 what? Who cares? And the other one is 24. Well, only thing you really know is this one is, twice as space complex as the other one. That's all you need to be able to know. Okay. Now, again, back in the day, and hopefully I won't be boring you with too many back in the day stories, but back in the day when RAM was expensive, and you had an MS-DOS machine that had 512 kilobytes of memory, then yeah, having a couple of arrays in there could be significant. That's not normally the case now, but when it comes time to comparing algorithms, it's still relevant. Okay, we're coming up on the 15-minute mark. You guys have figured out how this thing works. We're just going to stop this and then go to part 2.